I'm going to talk about Lagrangian matroids. If you don't know what a matroid is, you'll still be okay. If you do know what a matroid is, some of the little details in the talk will make a little bit more sense. But there's a lot of pictures, and you can just imagine that the kinds of matroids we're dealing with are going to be certain sets of pictures. So this is a problem that I was introduced to and worked on during a 2.5-month program for PhD students to leave the advisor for that time and work at it in some kind of discrete geometry tutorial thing. And that happened in Barcelona. So this was joint work together with Anna Gundert at ETH Zurich and Daria Schmura at Freie Universität Berlin. So we did this in Barcelona. How many people here have been to Barcelona? Lived in Barcelona? Okay, so here's a map of Barcelona. And I got very confused staring at this is the sort of a stereotypical tourist map that you get for free. And I got very confused staring at the tourist map of Barcelona and the kinds of things I printed out from Google Maps. Nothing seemed to match up. And there's a reason why. Does anybody know where north is on this map? If you raise your hand, you can't answer. Any guess where north should be? If you have your Barcelona geography. To the right, actually. To the right? Yeah, almost. Okay, so north is that way, right? Because Barcelona is on the coast, right? So this is what was confusing looking at my tourist map and the things that Google Maps gave me. So if you have a tourist map of Barcelona and you want to align yourself, you really have to rotate the map, right, 45 degrees or so. The reason is because, you know, if the maps are drawn with north being up, then about half of the map is just going to be water anyway, right? And no one's going to walk over there. Okay, so this will be important later. Just remember this. All right. I'm going to give you about half of the outline right now. And this half is just the definitions. So we're going to deal with matroids, but not very specifically, so I won't even define them. And then we'll deal with something that's sort of like a matroid, a different thing, for the purposes of this talk anyway, called a Lagrangian matroid. And then in front of each of these two things, we have this adjective, lattice path. Right? So we'll look at a special kind of matroid called a lattice path matroid. We'll look at a special kind of Lagrangian matroid called a lattice path Lagrangian matroid. So these two objects on the left are the ones that I really want you to understand. We'll have pictures, examples for these things. Okay? And if you know matroids, then this is, you know, we're looking at some special class of ordinary matroids, like, or some kind of generalization of a Catalan matroid. All right, so let's go ahead. The thing is, still, I'll introduce the KAIST in this order, lattice path matroids. Then we'll talk about Lagrangian matroids. Then we'll talk about lattice path Lagrangian matroids. Okay? So lattice path matroid. What is a lattice path matroid? Fixed two integers m and n. And I want you to look at the Cartesian grid. We're going to look at paths that go through lattice points in the plane. So what we do is go ahead and first fix a path called P, which goes only north and east. Okay, 1 unit at a time. It can only go up and to the right. It has to start at the origin and end up at the point m comma n. Right, so it's going to end up having n north-going steps. Okay, and then look at a second path called Q, which has to lie above P. And it can do some in the weak sense, like they could align for a while, but that doesn't happen in this case. And then what we're going to do is a lattice path matroid will be looking at all the paths that fit inside. So this purple path that's drawn in here is an example of a path that is also a north and east going path that fits between the red and the blue path. Right? And so we'll look at the collection of all of these paths, which include the red path and the blue path. And that collection of paths will be called a lattice path matroid. Okay, it's that simple. I want to note also, this sounds really stupid, but let's look at this purple path that's here, but let me also modify it and look at a different purple path. So purple prime will be go north, east, east, and then continue the same way. I want to emphasize that you need all such paths, and so there's a sort of no gaps property that we'll keep coming back to, which is if you have these two paths, the purple one and the purple prime one, then you're going to also need the one where you go east, north, and east. Right, so you can't have any gaps in here. You have to, if you have the one where you can go east, east, north, and continue, and the one where you go north and then east, east, and continue, you need to have the path where you go east, north, east, and continue.
So the blue and the red are fixed, and there are some of the purples. Some of the guys in the middle, and then there's some other purples.
No, we want all the paths in the middle. Okay? So the purple is one such path, but then the purple prime one that I just defined is another such path, but because you need all the paths, you also need the ones between the purple and the purple prime.
Okay.
And that would just be the one other path that I mentioned, the one that starts east, north, east, and continues. Right? So the lattice path matroid, if you don't know matroids, is going to be just a collection of all the paths between the red one and the blue one.
So when you say a path, it's a set of edges. I mean, what's the ground?
It's just a path.
So the ground set of the matroid.
Right, so that's the thing. So this is a matroid, and how is it a matroid? The ground set is the set of numbers from 1 through n plus n. And in a particular path, if you go north on the ith step, then I should be inside the basis. Okay? So the rank of the matroid is the height of this grid. And it's not too hard to, if you get bored, you can work out for yourself if the basis exchange thing works. Okay, so that's a lattice path matroid. What's a Lagrangian matroid? What we'll do is fix a number n and look at a set S of cardinality 2n. Okay, it has the numbers 1 through n, and it also has associated numbers 1 star through n star. One will be related to 1 star, but they're different. Okay, so this set S has cardinality 2n. And we'll say that a set B is a transversal if it contains 1 or 1 star, contains 2 or 2 star, 3 or 3 star, but always not both, right? So maybe a transversal, if n is 5, maybe a transversal something like 1, 2, 3, 4 star, 5 star. Okay. And if you have two transversals x and y, then I is a divergence with respect to x and y if I is in one and I star is in the other. So x might have 2, y might have 2 stars, so then 2 would be considered a divergence with respect to x and y. Okay? And what's a Lagrangian matroid? It will be defined by, we'll think of it in terms of some kind of basis version. So this is the basis axiom. And start with a collection of transversals, script B. Okay? And if the following, so you have to fix this thing in advance, right? If you're a matroid person, this isn't scaring you, but I just want to make sure you have to fix a collection of the transversals that you have in advance. So when is this thing, this set of transversals, going to be considered a Lagrangian matroid? It will be considered a Lagrangian matroid if the following thing happens for pairs, for any pair of transversals that you pick out of here. Okay, so what has to happen when you pick out two transversals x and y out of this set of things which you hope are going to be called the bases, and you have a difference between x and y, then there's another divergence, possibly different divergence, such that if you take x and you flip either I for I star. So if x has, what is this so much a difference to you, right? If you start with x, and if it has I, you have to replace it with I star. If it has I star, you replace it with I. And you do that same switch for j. Okay? If that new resulting transversal you have belongs in the set of the transversals which you declared you're going to look at in the first place.
So why doesn't play any role here?
Yes, it does.
Oh,
Why does play a role? Because the divergent, yeah, maybe I was trying to save some space on the slide, but divergence should always be with respect to transversals.
I see,
Right? So divergence here means divergence I with respect to x and y, divergence j with respect to x and y, and that should also go up here. Yeah.
What's the delta operator?
Yeah, this is symmetric difference.
What's that?
Symmetric difference. All it's doing right here is taking x, and if it has I, replacing with I star. If it has I star, replacing with I.
That's also for y, right?
Yeah, the same will have to hold for y, but it's just, I mean, divide it once this way, and it's fine.
So it's equivalent to delta matrix?
Yes. Yes, it is. Okay, so that's a Lagrangian matroid. You want an example of a Lagrangian matroid. Well, how about a lattice path Lagrangian matroid? Okay, so first there's a pictorial way to look at this thing too, okay? So let's do that first. So you start with a path, call it P, that goes up and down. But by up and down, now I mean it goes northeast and southeast, right? Root 2 steps at a time. So again, it goes through lattice points in the plane. Okay, so start with this kind of a path, call it P, starts at the origin. So of course, the sum of coordinates, whenever it goes to a particular lattice point, the sum of coordinates is going to be even, right? Okay. And then pick another such path that has to lie above. It can lie above in a weak sense. Call it Q. And now what we're going to do is look at all of the paths that fit inside here. Same kind of paths, up-down paths, so they'll never, ever possibly go through the point 1, 0, right? So we'll label that collection BPQ. Here's an example of one such path. Right? One such up and down path. Okay? And the collection of all such up-down paths that live inside the red and the blue, that live in between, that's going to be called a Lagrangian matroid. I mean, more than just a Lagrangian matroid, this will be a lattice path Lagrangian matroid. So why is a lattice path Lagrangian matroid a Lagrangian matroid? We won't prove that here. You can work that out again. But what's the correspondence you need? What's the n? That's the length of this thing here, right? However many steps you have. And what you need to do to each of these up-down paths is say, you know, if on the I step you go up, that means I star, and if on the I step you go down, that means I, or vice versa. It doesn't matter. So you just make that choice. Okay, so now we have all the definitions, right? So we've seen lattice path matroids, we've seen Lagrangian matroids, and we've seen lattice path Lagrangian matrix. It's just copied from the first slide. And the thing is, there's a certain relationship between matroids and Lagrangian matroids. You'll see that in half a slide. So the question was asked by Anna Demir, what is the relationship between lattice path Lagrangian matroids and lattice path matroids? For instance, do they share the same connection that these two do? Okay, so that's the question we investigated in Barcelona. What exactly was this connection? It's right here, and I'm really terribly sorry for this, shoving this amount of notation into a slide, but here's how it goes. So start with a collection of transversals, okay? And we need to understand quickly this definition first, this IDT thing. So how does it work? You start with a fixed collection of transversals and one other fixed transversal T. Okay? By the way, this transversal T doesn't have to belong to this collection B. So you pick two things. You pick a set of transversals B, and you pick one more transversal T, possibly in the set, but possibly not. And what do you do? For every transversal regular B that's inside this set, script B, you do the following. You intersect it against this transversal T. Remember, these are both sets, right? They're both subsets, they're n-element sets. So you just take the intersection, and every subset you have that you get out of this way, you throw that in, right? Every single subset you get, you call that one of these i's, and that is the kind of thing that belongs in here. And you run the same experiment for everything that is in the collection of transversals you started with. And this is quite a bit to swallow, I realize. I mean, you just have something. We'll play with this more in a second. But here's this connection, right, between matroids and Lagrangian matroids. This set that you started, this collection of transversals, is actually not just a collection of transversals, but is a set of transversals which satisfies that symmetric exchange axiom, namely is a set of bases of a Lagrangian matroid, if and only if this ugly set here is a set of independent sets of an unoriented matroid. Okay, so if you want, and you know what all that means about independent sets of a matroid, this characterization gives you just an equivalent definition for what a Lagrangian matroid is. So the natural question to ask, of course, is, well, fill in this little actual physical gap of space here, right? So the conjecture is, does the same relationship hold for lattice path matroids and lattice path Lagrangian matroids, right? And what we investigated was that, this conjecture came about, I mean, not only just out of blind guessing and whatever, but Demir had done some calculations to show that in certain cases, this forward direction seemed to be true. So for certain collections of lattice path Lagrangian matroids, you could get this to work. But is this true in general? Well, we were able to show that the reverse direction does not hold in general. But the forward direction is indeed a theorem. Okay? So this works for all lattice path Lagrangian matroids. And the plan is to sort of roughly sketch out two ways to prove this. One a bit more existential, and then one that's more algorithmic. And both kind of give us some insight on some more things we would like to do with this. So what are we going to try to do now, right? We're going to take this and start with a collection of bases of a lattice path Lagrangian matroid. Or in other words, we fix a path P, we fix a path Q, we look at all the paths that fit inside, and then we want to understand this set, IBT. But right now, this set is about independent sets. And it requires, I mean, not so much of a quoting some matroid theory, just to say, we want to actually look at the largest independent sets, because those will be the ones that are the bases. Right? So let's actually understand that much more slowly on the next slide. Note the thing is, again, we need to deal with this fixed transversal. Right? So we have to understand the set, but it involves a transversal T. We need a reasonable way to actually do this geometrically, and it goes like this. So let's understand this IBT, and let's understand its largest sets, the ones that are called the bases. So fix, first of all, a P and a Q, a blue path P, a red path Q, and you have all the paths in between as before. We fixed some transversal T, and at first we were trying to draw T as an up-down path inside here, and that made no sense. That's not the way to think of this fixed transversal T. The better way to think of it is as some sequence of up-down arrows which you just kind of draw above the whole thing. Okay. This turned out to be the right way to think about this. And so we want to ask, what are the bases? Right? What are the largest sets in terms of cardinality in this set? Well, first of all, here you keep taking subsets, so let's not do that nonsense. Right? Let's just look at, don't look at any proper subsets, just look at B cap T. Right? But what kind of B's are going to be the winners? Which kind of B's, those are again the paths correspond to the paths in here, which paths are going to give us the most intersection with T? Intersection with T means that T would have one star if it's going up, and your path B would have one star if it's also going up. Right? So we're looking to increase the cardinality of this B intersect T as much as possible, meaning we want to look at paths which go in the same direction as T as much as possible. So to put it more shortly, we're trying to look at paths being inside the red and blue path that agree the maximum number of times with t. Right? So what I've done in this is I've superimposed in black all of the maximal paths. So as long as you start at the origin and just keep walking rightward and of course also up and down, then any such path here in black is going to be a maximal path. So if you see, for instance, there's a black path that is basically just the red path here, right? It agrees with t on the first 1, 2, 3, 4, 5, 6, 7, 8, 9 steps, and then it just disagrees with t in the last 2 steps. Right? So all the black paths here have 9 agreements. We could find no path between the red and the blue that agreed with t 10 times. 9 is the most you can do. Okay? And for short, we'll call these black paths here maximal paths. So to do our existential proof, we needed to understand the structure of maximal paths a little bit. So we had a couple lemmas. One is that suppose you have that 2 maximal paths cross each other. Right? If that's the case, they have the same number of agreements with t up to the point of cross. Once they cross, they have the same number of times that they agree with t. So it makes sense if you started with this, purple and blue path, and you had this orange and then red path, to instead also look at this purple and red up-down path, and to look at this lower one as well. And those would also be maximal paths. Right? So for us, it makes sense if you look back here, you can have this kind of gap where the 2 boundary paths don't have to line up and close at the end, but it makes sense to make sure that, it made sense to just not worry if there was any gap here, to just close this up, and to always look at saying, well, that's just silly, let's just always, there's a sense of a highest maximal path and a lowest maximal path, and we'll just always look at those. Okay, so that concept is well defined. The other thing, which I kind of already hinted at, is that all maximal paths have to end at the same point. So what do I mean? Suppose you had 2 paths, S and R, here in red and blue, that agreed with t, they're maximal, so they agree with t the same number of times, but they didn't end at the same point in the plane. Okay, so without loss of generality, let's say this red one, has a height that's higher than the blue one on the very last step. This can't happen, so we argue this can't happen by contradiction. What happens is we should pay attention to those columns where the red and the blue path disagree from each other. So we highlight them here. And in these places where there's disagreement, well, the lower path has to go down on there must be at least one place where the lower path goes down where the path that ended up resulted higher goes up. Right? So we look at one of those places, and all we do instead of going down here is we take this path and we go up instead, and then just otherwise do exactly what the blue path had done on each step, on each subsequent step. Right? When you do that, this new purple path, which otherwise follows the blue path, has one more agreement with t than the blue path did, meaning that the blue path couldn't have been a maximal path. Okay, so this is how you close the gap. So this is how you also know that if you follow along any of the maximal paths, any path that agrees with t the maximum number of times, you're always going to end up at the same final destination. Okay. We had a couple other structural lemmas which were a lot harder to actually prove, so I skipped the proof. I'm going to tell you just what happens. This was really one of the most shocking things we noticed, was that when you superimpose all of the maximal paths, like we had seen pictures of all the ink in black, and let's say you just look and study one column at a time. You look at what you see in the superimposition of all the maximal paths, you see 2 kinds of phenomena. Either you see this, where you have, there should be black actually right here, I'm sorry, but you have a piece of a path right here, and then you go 2 units down, and you have that same piece of a path, and you go 2 units down, and you have this. You basically have this parallel train tracks-like look, which we call a parallel step. Or you have this zigzag. So if you look, you just focus on a particular column, the superimposition of all the maximal paths has this particular shape. Meaning that if you were working this out by hand and you saw that you had a maximal path that went through here, right? From this point to this point, and you knew you had another maximal path that went from here to here, and assuming the red and the blue path are the highest maximal and lowest maximal paths, then you could just keep drawing the rest of this zigzag in. You would have to be there. Okay. So what I want to do is sort of take the facts of the last 4 lemmas, I think they were, and summarize. So we can assume, so what do we want to do? We want to take a lattice path Lagrangian matroid and construct out of it a lattice path matroid. Meaning we want to take each of the maximal paths and show that it corresponds to some path in the lattice path matroid. So we need to construct the boundary paths, the red and the blue path, for the original kind of matroid we saw, right, with the north and the east steps. So one easy assumption we can make is that these two, the lowest and highest maximal t paths, don't meet until the last step, because otherwise you could just take a Lagrangian matroid direct sum. Okay. And we can actually just assume we don't have any parallel steps. Now this is fairly easy to see once I just say, well, what happens in a parallel step? In a parallel step, if the ith step is a parallel step, then all of the maximal paths, well, they have the same behavior, right? They all either go down on the ith step or they all go up on the ith step. And in particular, they all either agree with t or they all disagree with t. And the point is that in those kinds of steps, you can just record that information last in your lattice path matroid. So in your lattice path matroid, we had the basis elements, the things that give you rank, are the steps that go north, and you can just, if agreement with t gives you greater cardinality, right? So all you can do is say, well, if you have a parallel step that's an agreement with t kind of step, you can just record that as a north step for all paths last, or something like that. Right? So with these assumptions, what do you have? You have that if you get rid of the parallel steps, that means that you just have all these zigzags along all the columns. And it means that between the red and the blue boundary paths that you have, which meet up only at the end, all the paths that you can draw inside here are going to be considered t maximal paths. Okay? And with sort of, column by column surgery, you can also assume that the fixed transversal t that you have is just doing the all, up step thing. Okay? So remember, what we're trying to do is take a lattice path Lagrangian matroid and find a lattice path matroid, right? We need something that has only, pure north and pure east going steps, that closes up, meets at the same point, and that would be a lattice path ordinary matroid. So where are we going to find that? Anybody remember the first step? We did this little Barcelona transformation, rotate by 45 degrees. So there it is. Okay? So it's a bit of an existence proof of how we get this thing. If we can do something more step-by-step, more iterative, we can maybe see how some of the other things behave with relation to the matroid. So I want to waste your time for a moment by reproving the theorem or sketching a proof of the theorem from a completely different view. So if you don't like these lemmas, you're going to get something more of an algorithm right now. Okay? So great. What we just saw was that taking all the maximally agreeing paths, you can basically draw, each one of them as a particular north and east going path, and the collection of all of them end up magically having no gaps so that you end up having a lattice path matroid. Right? That's what we just saw. Now our task is going to be to just actually compute these boundary paths that determine the LPM specifically, okay, explicitly. So how we're going to do this is by, some kind of induction on the length n. Okay? So if you have a lattice path Lagrangian matroid of just one step, well, everything's very easy. You can work it out in your sleep. So what we do is, right, we assume that we've already built up, we have our lattice path Lagrangian matroid, we've built the corresponding lattice path matroid up to a certain number of steps, and now we want to extend the lattice path Lagrangian matroid by one more step and say, well, it doesn't matter what we do in the last step with the boundary path, it doesn't matter which way t is pointing up or down. No matter what happens, we can build the corresponding lattice path matroid by taking the one we already had by induction and modifying it slightly. Right? That's what we're going to try to do. And I claim that we can assume, for writing down this algorithm or something, that the last step, the new step that we're looking at, t, this fixed transversal, is pointing up. Why? If it's not, if you have this painful situation where this last guy is pointing down, what do? You just flip everything, right? You just star all of these. So all the down rows are up and vice versa. Otherwise, for the paths and all the paths that are inside here, you flip, in a geometric sense, everything. In fact, the role of P and Q change as well. Right? Which one is the lower path is different now. But the point is, everything still makes sense here, right? So all of the agreements are still the same. So what you had drawn previously for your LPM up to this point, for n-1 steps, is going to work out just fine. Okay? So great, we can assume this. And there's more or less two cases which, one I call the easy, one is the hard. And what is the easy case? It's sort of represented right here. Right? So the easy and hard, by the way, in terms of the matroid, the LPM, it's something about whether the rank of the matroid grows by 1 or remains constant. So in this case, the easy case, what happens is, let's say we've already built by induction everything up to right before the last column, right? So we have this much of the lattice path Lagrangian matroid, and by induction we know the corresponding lattice path matroid. Now we made a choice of how to extend by one step the red path, the blue path, and you made a choice for t. Right? And this is the easy step, I claim, because all you do is you look at that unique point, remember where all of the maximum paths had to end. They all had to end at the same place. And you notice that all you need to do is just from here, just change all of these paths by declaring that they should all go up on the last step. Remember, we're trying to find steps that agree with t the most number of times possible. Right? So if you do that, then everything's good, right? You get one more agreement with t, and it takes not too much work to convince yourself that you couldn't have done any better than that. So that's the easy case. In fact, it's also very easy to see how the lattice path matroid would have to change. All you do is either at the beginning or the end, you just say, well, I'll just extend my drawing for the lattice path matroid. The boundary paths should just both go north on the first step or something, right? Because that's just encoding an agreement. So if that's the easy case, then what's the hard case? The hard case is when you look at that unique point where all of the paths end, the common ending point, and you can't go up on the last step. And the reason you couldn't go up on that last step would be because, say, this red path that you picked it incorrectly and it goes down. Okay, so you can't easily extend and just say, well, they should all go up. Well, you first prove that, even though you have 9 agreements here, there's nothing else you could have done, even in this situation, to get more than 9 agreements. So you give up, you say, all right, but I still don't have paths of the right length. The length is 1 too short right now. So how do I find the paths I have that are also still agree 9 times? Well, first of all, these paths that you've already drawn, if you just disagree with t on the last step, those are some paths that you want to hold on to. right? But it turns out that in this more difficult case, there are other maximal T agreement paths that you haven't seen before. Where are they? What you do is you take a little snake and you just follow it below the lowest maximal path you know. And you just keep traveling as far as you can go until the snake runs out of room. And it always happens to be the case that wherever the stop occurs, the lowest maximal path you know happen to agree with T, right? Now, why did we draw this? What you should notice is that, let's say you follow along the bottom of this, where this pink region is. Okay? And I want to say that this should be a good path for us. It should also be a 9 times agreement kind of path. Where should we look first? We should actually look at the end. That's where we should look first. Okay, so all the other paths in the new last step, they disagree with T. Well, this path, if you follow along the bottom of this pink region, the path that would go up here agrees with T in the last step. And so that's good. We got an agreement with T. Otherwise, it's copying what the previously known lowest best path did. And because we had that one extra agreement early, we paid, we can slack off earlier on. So it's at this step where this previous lowest best path went up and agreed with T, we're now allowed to disagree with T. Right, so this, now if you just follow along what's in blue until up to this point and you follow up with the pink, this is going to be another path that agrees with T 9 times. But this isn't the only such path. Right? So if you notice, there's other paths other than this one that's highlighted in green that will work. Because, well, what do? You take your old lowest maximal path, and you can note that basically you can disagree earlier somewhere. And it's just geometry just to say what places you can disagree earlier. It's just, you have to be able to go down, right? And so these are places that you can't go. Like, so if you start here on the lower path, you don't want to go up here because that's going to create a disagreement with T too early. But along these green pieces, you can travel from starting on the black curve and then travel down along any of those green segments. And so any of those paths are going to be good ones. So if you will, with me, the superposition of all the black and all the green, those are going to be all the new maximal paths. Still 9 agreements. So therefore, if you're a matroid person, the corresponding lattice path matroid should have the same rank, or the height of the grid shouldn't grow. Okay, so in the case that the rank remains the same, that's this case. Well, what happened? Remember the story here was, this is the new column. You can't go up. It's not the easy case. We had this snake down. Here was, by induction, the lattice path matroid we had before. What do the numbers indicate? It indicates which step along here you're encoding, right? So the reason that the 4 is here is because you'll notice that the 4th step is a parallel step. Right? So you have to encode this stuff in the beginning over here. I'll talk about that in a second. This little piece that we added right here corresponds to this, right? So on the last step, your choice of northeast or southeast, we know that we can't go northeast, right? That would spill outside of the boundary region. And so we have to go down. That disagrees with T, and disagreeing with T means we shouldn't add to the rank or to the basis, so we should go east. So this new 11th step we record is going east. And then all of this new path that we discovered, well, what happened here? We got to disagree earlier. So where did we record the second step? Previously, it was recorded right here that the second step had to go up. But now, we know that the second step can disagree. And so this piece of the red path that's highlighted, that corresponds to this in the lattice path matrix. So the only thing that's left to do is to make sure that, remember this no gaps thing, right? That's the key thing. Anyone can just say, well, let's start with something over here and say that every path over here, just draw a path over there. But that's not good enough. You have to make sure that every path you have that's in these what are currently potential gaps is achieved by some path over here. And so all of these gaps are plugged in by disagreeing earlier. Everything works out nicely there. Okay? And if you even really want these pink boxes, including these sort of longer pink boxes, correspond to each of the regions here in a very natural way. Now, I want to comment that this is exactly this numbering thing of saying that, we start by recording what happens here instead of recording what happens on the first step over here, we're recording first what happens on the fourth step. This is necessary because if you try to put this in order and record the first step first and the second step second, everything's okay until you get to the fourth step. But then you would have, for the fourth step, since everybody has to go the same way, namely all the steps have to agree, you would have these two, parallel pieces going up, but then you couldn't fill in the gap. So the original theorem that I showed you is only true, in a sense, up to some kind of matroid isomorphism. Okay? But that's it, that's the construction. And so this is the final picture, right? And the point is you can continue this by induction. Now, what kind of thing would we like to know? Well, there's a researcher in Kansas, Jay Schweig, who showed that for these kinds of matroids, it's easy to read off what the H vector is. All you do is H sub I, I'll probably get this wrong, but more or less, H sub I is going to be the number of paths which touch so you have the upper boundary path, the one that was labeled in red earlier. H sub I will be the number of paths which touch the red path exactly I times. So by following along, by having the LP11 and the LPM side by side and constructing them slowly, there should be some corresponding H something over here, so that that H thing, together with the transversal T, should allow you to recover the H vector on the other side for the LPM. But I have no idea what the object is, and much less how to actually do it. So if you have any idea, I would like to know. Otherwise, I think that's it. So, thank you very much.
Do you have any questions?